Level 1. Kinetic energy. Kinetic energy is the energy an object has because it is moving. A rolling ball, a flying airplane, a flowing river, and even the molecules moving through the air all possess kinetic energy. The amount of kinetic energy depends on two things: mass and speed. A heavier object has more kinetic energy than a lighter object moving at the same speed. However, speed has an even greater effect because kinetic energy increases with the square of velocity. This means that doubling an object's speed gives it 4 times as much kinetic energy, while tripling its speed gives it 9 times as much. Kinetic energy can also be transferred between objects. When one billiard ball strikes another, some of its kinetic energy moves into the second ball. During real collisions, some energy may also become sound, heat, or deformation. Although the visible motion can disappear, the total energy does not simply vanish. Level 2. Gravitational potential energy. Gravitational potential energy is stored energy caused by an object's position in a gravitational field. Near Earth's surface, lifting an object higher gives it more gravitational potential energy because gravity can accelerate it through a greater distance as it falls. The amount of gravitational potential energy depends on the object's mass, the strength of gravity, and its height relative to a chosen reference point. A book on a high shelf has more gravitational potential energy than the same book on the floor. A heavy rock at the top of a hill also stores more energy than a small pebble at the same height. When an object falls, its gravitational potential energy is converted into kinetic energy. At the highest point, it has more stored energy and less motion. As it moves downward, it loses height and gains speed. This continuous exchange helps explain falling objects, roller coasters, hydroelectric dams, and the motion of planets and moons. Level 3. Elastic potential energy. Elastic potential energy is stored when an object is stretched, compressed, bent, or twisted. A stretched rubber band, a compressed spring, and a drawn bow all contain elastic potential energy. When an elastic object is deformed, its internal particles are pushed away from their preferred positions. Forces inside the material resist this change and attempt to return the object to its original shape. Releasing the object allows the stored energy to become kinetic energy. A compressed spring can launch an object forward, while a stretched bowstring can accelerate an arrow. However, materials have elastic limits. If an object is stretched or bent too far, it may not return to its original shape. It can become permanently deformed or break, with some of the stored energy becoming heat and sound. Elastic energy appears in clocks, trampolines, vehicle suspension systems, toys, sports equipment, and even the tendons inside the human body. Level 4. Thermal energy. Thermal energy is connected to the microscopic motion and interactions of particles inside matter. Even when an object appears completely still, its atoms and molecules are constantly vibrating, rotating, and colliding. The faster these particles move on average, the higher the object's temperature usually becomes. Temperature and thermal energy are related, but they are not identical. Temperature measures the average kinetic energy of the particles, while total thermal energy also depends on how much matter is present. A bathtub of warm water can contain more thermal energy than a tiny cup of boiling water, even though the cup has a higher temperature. Thermal energy naturally moves from hotter regions to colder ones. This transfer can happen through conduction, convection, or radiation. Friction can also convert organized motion into disorganized particle motion, which is why rubbing your hands together makes them warmer. Thermal energy is involved in engines, weather, cooking, climate, and nearly every physical process around us. Level 5. Chemical energy. Chemical energy is stored in the arrangement of atoms and electrons within substances. During a chemical reaction, existing bonds are rearranged as atoms combine in new ways. This process can release energy into the surroundings or absorb energy from them. Fuel contains chemical energy that can be released through combustion. When gasoline reacts with oxygen inside an engine, some of its chemical energy becomes thermal energy, which produces expanding gases and eventually mechanical motion. Batteries also store chemical energy, but they release it through controlled reactions that push electric charges through a circuit. Food is another major example. Plants use sunlight to construct energy, rich molecules through photosynthesis. Animals then break down those molecules through cellular respiration, providing energy for movement, growth, repair, and body temperature regulation. Energy is not literally stored inside a single chemical bond like an object inside a box. It comes from the energy difference between the complete arrangement of reactants and the complete arrangement of products. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. Level 6. Electrical energy. Electrical energy is associated with electric charges and their positions or movement. Electrons and protons create electric fields, and these fields can exert forces across space. When charges move through a conductor, we describe that movement as an electric current. A battery creates a difference in electric potential between its two terminals. When a complete circuit is connected, this potential difference drives electrons through the circuit. The electrical energy can then be transformed into other forms. A lamp converts it into light and heat, a speaker converts it into sound, and an electric motor converts it into mechanical motion. Electricity is not necessarily a stream of energy traveling at the same speed as individual electrons. The electrons in a wire usually drift quite slowly, while changes in the electric field can spread through the circuit extremely quickly. Electrical energy is especially useful because it can be transported, controlled, and converted with great precision, making it essential to modern technology. Level 7. Radiant energy. Radiant energy is energy carried by electromagnetic waves. Visible light is one example, but it represents only a small section of the electromagnetic spectrum. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays are all electromagnetic radiation. All electromagnetic waves travel at the speed of light in a vacuum, but they differ in wavelength and frequency. Higher frequency radiation carries more energy per photon. Radio waves have relatively low frequencies, while X-rays and gamma rays have extremely high frequencies. Radiant energy does not require matter to travel through, which allows sunlight to cross the vacuum of space and reach Earth. When radiation interacts with matter, it can be reflected, transmitted, or absorbed. Absorbed light may become thermal energy, trigger a chemical reaction, or generate electricity in a solar cell. Nearly all energy supporting Earth's climate and ecosystems originally arrives as electromagnetic radiation from the sun. Level 8. Sound energy. Sound energy is carried by vibrations traveling through matter. Unlike electromagnetic radiation, sound cannot move through a perfect vacuum because it requires particles to pass the disturbance from one location to another. When a speaker vibrates, it repeatedly pushes and pulls the surrounding air. This creates regions of higher and lower pressure that travel outward as a wave. The air itself does not travel all the way from the speaker to the listener. Instead, nearby particles oscillate around their normal positions and transfer energy to neighboring particles. The frequency of a sound wave determines its pitch, while its amplitude is connected to how intense or loud it is. Sound travels at different speeds through different materials, generally moving faster through solids than through gases because the particles are more strongly connected. Sound energy is usually small compared with other energy forms, but it is essential for communication, music, medical imaging, navigation, and studying distant events such as earthquakes. Level 9. Nuclear energy. Nuclear energy comes from changes inside atomic nuclei. The nucleus contains protons and neutrons held together by the strong nuclear force, one of the fundamental forces of nature. Rearranging these particles can release far more energy than ordinary chemical reactions. Nuclear fission occurs when a heavy nucleus splits into smaller nuclei. Some of the original mass becomes energy, while additional neutrons may trigger further reactions. Controlled fission chain reactions are used in nuclear power stations to produce heat, which boils water, turns turbines, and generates electricity. Nuclear fusion works in the opposite direction by joining light nuclei into heavier ones. Fusion powers the Sun and other stars, where extreme temperatures and pressures allow hydrogen nuclei to combine. Fusion can release enormous amounts of energy because the final nucleus has slightly less mass than the original particles. That missing mass has not disappeared, it has been converted into energy according to Einstein's equation, E equals mc squared. Level 10, mass energy. Mass itself is a concentrated form of energy. Einstein's equation, E equals mc squared, states that an object at rest possesses energy simply because it has mass. This is called rest energy. The speed of light squared is an enormous number, so even a tiny amount of mass corresponds to a tremendous amount of energy. In most everyday processes, the mass changes are far too small to notice. Chemical reactions technically change the total mass of a system, but the difference is usually microscopic. Nuclear reactions produce more noticeable changes because much larger amounts of binding energy are involved. Mass and energy are not two completely separate substances. They are properties of one physical system and can be transformed while the total mass energy remains conserved. A particle can meet its antiparticle and convert their rest energy into radiation. Sufficiently energetic radiation can also produce new particles. At this level, energy is not merely something objects possess while moving, heating, or reacting. It is woven into the existence of matter itself.